We were looking at the Solow model. We discussed the setup. Then we discussed how do we write the production function in per worker terms. We now want to see how do we write a capital accumulation equation in per worker terms. The capital accumulation equation, as we saw, was this, right? Kt plus 1 is equal to 1 minus delta Kt plus I. Right, so we want to see how do we write this capital accumulation equation now in per worker terms. So we want to write that capital accumulation equation in per worker terms to describe the evolution of capital per worker over time. So we want to essentially write change in capital per worker as a function of capital per worker in parameters. The way we'll do that is we'll use our per worker production function, which we just learned before. How do we write our production function in per worker terms? We learned this over here. So we'll use our per worker production function, and our savings is equal to investment identity to reduce everything in our capital accumulation equation in terms of capital per worker and our parameters of our model, like the savings rate and depreciation. We don't want the capital accumulation equation to either include investment or output. So what we're going to use, the two things we're going to use is our per worker production function and our savings is equal to investment identity. The per worker production function we looked at over here. How do we write a production function in per worker terms? And the savings investment identity we looked at over here. Savings investment identity. Investments is equal to savings, which is proportional to income. So we'll use this identity along with our per worker production function. So now how will we go about doing this? Now this is our capital accumulation equation. Capital next period is equal to undepreciated capital of this period plus investment. So the first step is that we're going to use our saving investment identity. Like we said, we're using two things. Savings is equal to investment identity and per worker production function. So the first step is to replace IT with SYT, right? So we're using our savings investment identity if investments are equal to savings, which are proportional to income by assumption. So replace IT is equal to SYT, because remember the goal is to write this in per worker term, where you want to express everything in terms of capital per worker and parameters of the model. We don't want IT to play in this model. So I'm going to replace IT with SYT. So then this becomes this KT plus 1 is equal to SYT plus 1 minus delta KT. And since we want to write it in per worker terms, we'll divide both sides by n. So note over here, n does not have a time subscript like k and y. This is because we're assuming n is fixed. Right, we're looking at the Solow model without population growth right now, which means that n is fixed, so nt is just equal to n. So the reason we don't have a time subscript with n over here is we're looking at the Solow model without population growth, so n is fixed. So we're writing both sides by n because we want to write the capital accumulation equation in per worker terms. So we're going to rearrange this a bit, and I can write it like this. Kt plus 1 by n minus kt by n is syt by n minus delta kt by n. So we just separated this term. We've taken the kt by n part there and minus delta kt by n part stays here. So we just rearrange this a bit to get capital per worker on the left-hand side. Because again, the goal is that we want to write change in capital per worker as a function of capital per worker and parameters of the model. So now what we're going to do is, like we said, we want everything in terms of capital per worker and the parameters S and delta. We don't want I or Y present in this capital accumulation equation. We removed I, but that introduced Y. Now we want to remove I. So for this, we'll use our per worker production function. Like we said, we use two things. Savings is equal to investment identity, which we used in step 1. And now we'll use the per worker production function. So replace YT by N with the per worker production function FKT by N. So now we can see that everything is in terms of capital per worker and our parameters of the model. So now I can just let KT plus 1 by n equal to small kt plus 1, because here the notation we're using is that uppercase letters are denoting aggregate variables and lowercase letters are denoting per worker variables, as we saw before also. Like uppercase letters denote aggregate variables and lowercase letters denote per worker variables. So, and then small kt, kt by n is equal to small kt. So then I can write this as change in capital per worker from year t to year t plus 1 is equal to investment per worker, which is or equivalently savings per worker during year t, because remember investments are equal to savings in this model given our assumptions, minus depreciation per worker during year t. And sometimes this term delta KT, which is depreciation per worker, is also known as break-even investment per worker, which represents the amount of investment necessary to keep capital per worker constant in the face of depreciation, which tends to reduce the amount of capital per worker in the economy. So we're saying change in capital per worker is equal to investment per worker, equivalently savings per worker, minus depreciation per worker, which is also sometimes known as break-even level of investment per worker. So everything now has been reduced in terms of capital per worker and in terms of the parameters of the model. So we have been able to write the capital accumulation equation in per worker terms to describe the evolution of capital per worker over time, i.e. express change in capital per worker as a function of capital per worker and parameters of the model. So in per worker terms, this was a capital accumulation equation. Change in capital per worker is equal to investment per worker, which is or equivalently savings per worker, minus depreciation per worker, which is also known as break-even level of investment per worker. Now, the interpretation of this equation is that if investment per worker exceeds depreciation per worker, so then change in capital per worker is positive, so capital per worker increases over time. Investment per worker is more than enough to compensate for the capital needed for depreciation. But if investment per worker is less than depreciation per worker, the change in capital per worker is negative, so capital per worker decreases over time. Investment per worker is not enough to compensate for the capital needed for depreciation. So there are two key equations in the Solow model. One is the production function in per worker terms. The other is the capital accumulation equation in per worker terms, which allows us to describe the evolution of capital over time by expressing capital change in capital per worker as a function of capital per worker and the parameters of the model S and delta.